conductor, it generates magnetism around it. That's what the whole objective of this chapter is. Okay, like as I told you in the previous class, in your 10th grade, you would have learned about drawing the field lines around different, how to draw the field lines around different types of conductors and all those things. But this year, that is your 12th standard, will be interested to calculate what is the magnitude, that is what is the value of the magnetic field that is getting generated due to a particular amount of current at a particular location. Okay, so that law was proposed by Biot-Savart, and last class we saw its application also. So Biot-Savart law states like this. So what is it? So when you have a current carrying element in your hand, right? When you have a current carrying element, so what is the difference between current carrying element and current carrying conductor? Current carrying conductor is going to be the whole length. Current carrying element is going to be an infinitesimally small value on the particular conductor, right? Which is going to be dl. So if you have a small infinitesimally small current carrying element present on a particular conductor, if you want to calculate the magnetic field at a point P, which is at a distance r, okay, let's say the radial vector is making an angle theta with respect to the current carrying conductor, then the value of the magnetic field due to the small current carrying conductor is given by the formula mu naught I dl sin theta divided by 4 pi r square, where I stands for the current flowing through the conductor, dl stands for the length of the current carrying element, sin theta, theta stands for the angle between the current carrying element and the radial vector, and r is the distance between the current carrying element and the point where we are trying to calculate the field. And one more important point that I stressed last class is how to find the direction of magnetic field. So there are two rules that you can use to find the direction of magnetic field. One is right hand thumb rule. So what does right hand thumb rule state? When you have when you place the thumb of your right hand in the direction of the current and curl the fingers as if you are holding it. Let me show this part for you to recollect. So I'm switching on my video. See, when you have a current carrying conductor, if the current is flowing in the upward direction, you place the thumb of your right hand in the direction of the current, and curl the fingers as if you are going to hold the conductor. When you hold it, the direction in which the fingers of your right hand, so please make it a clear point, don't put your left hand, you will get the wrong answers. So the direction in which you're curling your right hand gives you the direction of the magnetic field at that particular location, right? So that is what is right hand thumb rule. Also, there is another rule to find it. One is that is using the cross product. So how do you use the cross product? So we know the vector form, right? So what is the vector form of Biot-Savart law state? It is like this: dB vector is equal to mu naught I into, I'll show you this. So mu naught I into dl vector cross r vector divided by r cube. I hope you made a note of this, right? So dl vector cross r vector is going to give you the direction of the magnetic field using the cross product of vectors. That also we have seen, right? And the last concept that we saw in the last class is application of Biot-Savart law. We saw magnetic field due to a straight current carrying conductor. That was the first concept which involved a bit of integration in your 12th standard, right? I hope things are clear there. So what was the answer? We got the answer as mu naught I divided by 4 pi into sin phi 1 plus sin phi 2. This is the answer we got: mu naught I divided by 4 pi into sin phi 1 plus sin phi 2, and you did few problems. Now what we are going to do is, we are going to see the next application of Biot-Savart law, which is there in your textbook. If you have your NCERT PDF, it is there in page number 145, the topic 4.6. Okay, the topic is magnetic field on the axis of a circular current carrying loop. Okay, I'm repeating it again: magnetic field on the axis of a circular current carrying loop. Means what will happen here is, you will have a circular loop. Okay, I've taken a small bangle. So you will have a circular loop. In the circular loop, the current can either flow in the anti-clockwise direction or clockwise direction. Okay. So for this circle, this is going to be the center. I hope you are able to see it. So for the circle, obviously you know which point is the center, the point where you place the compass and draw the arc. So that center. So from the center, observe it clearly. If I take, from the center, if I take any point perpendicular to the circle, then that point is called as the axis of this particular circular coil. Okay. Now what is our job is, the current is going to flow through this wire. Okay. At some point on the axis, that is at some point on this, at some point on the axis, we need to find what is going to be the value of the magnetic field due to this particular system. Okay. Is there everyone who is Are you able to visualize it? If so, just give me an S in the chat box, because that's the first step you need to visualize. Okay, that's good. Okay, we'll get started. So let me put this diagram. See, you have to visualize this part. Okay, so we are using the word circular current carrying loop. Look at your textbook. We are saying the term circular current carrying loop, but when you look at the diagram, no, the diagram will be in the shape of oval. The reason being, it is like this. So if you see the circle in a two-dimensional plane, okay, that is, if I place my hand, I'm taking this as the x-axis and this as the y-axis. If I place it in the two-dimensional plane, you will be able to see a completely circular part. Okay. If I place it perpendicular to this two-dimensional plane, then what will you see is, you will be able to see only this part, which is nothing but a straight line. Okay, you can see it like a straight line when it is exactly perpendicular to the two-dimensional plane. Now there will be one particular scenario where neither it is perpendicular to the two-dimensional plane nor it is exactly in the two-dimensional plane. You can place it like this. So I hope you are able to see it. When you place it like this, you can see that shape of the circle will be like an oval. So for this oval shape, the axis is going to be somewhere over here. This is going to be the axis. A line which is passing through the center and perpendicular to the plane of the circle is what is axis. At some point we are going to find that. Right? Let me draw that diagrammatically. Since we have seen how it looks, let me draw it diagrammatically. I'm switching off my video. There is any doubt, let me. Okay. See, this is slightly a tricky concept. I want you all to concentrate properly. So please get it clarified. So the heading, write it down. Magnetic field on circular current carrying loop. So the heading is magnetic field on the axis of a current carrying loop. Okay. Someone's audio has got switched on. Please mute it.
Sir,
yeah, who's this?
Naveen here.
Naveen, tell me.
Sir, so the axis is passing through the center of the plane and is also perpendicular.
Okay.
It's a clarification.
No. See, center is a point. There is nothing like center of a plane. The plane doesn't have any center. Only the circle has the center.
Okay.
Okay, when you're using the word, please be clear about it. Point is going to be represented as the center. Point doesn't have any dimension. You cannot say it is one dimension, two dimension. So point I'm trying to talk about is the center of the circle. See, look at my hand. What I've done is I've exactly passed it through the center and placed it perpendicular. See, if you ask me, it is like this. You are able to visualize this red color. You are able to see this?
Yes, sir.
I'll show it. Yeah, I'll show it like this. See, maybe I'll show it like this. You are able to visualize it better?
Yeah.
Yeah, you got my hope. Yeah. Somewhere on this pin is what is called as the axis. It can be at any distance. That is what I'm trying to find out. Okay?
Okay.
Yeah. So, listen. So, you have a circular current carrying loop. Okay? The current, I taken it to be in the anti-clockwise direction. I've taken the current to be in the anti-clockwise direction. I'll tell you how to visualize it. Please pay some attention. If I take this point to be P, so this is going to be the center of the circle. Let me call the center. I'll exactly go with the diagram of the textbook. This point is O, and let me take this point P, which is the distance x from the center. Okay. Now, remember, this current carrying loop is hollow in between. Like how I showed you the bangle, it is having only the circumference, and the current is flowing only through the circumference. And I've taken it in the anti-clockwise direction. So, how to visualize actually it is in the anti-clockwise direction is, they give a diagram, no? They give it like this. If you observe in the exam, when they give it, so I'll draw it like this. Okay, the same loop I'm drawing it in this way, and I'm trying to say you have a continuous line and a set of dotted lines, right? So the continuous lines are the ones which are close to you, and the dotted lines are the ones which are away from you. Okay, if I put an arrow mark in the downward direction for the closed loop, for the continuous loop, then you can say it is in the anti-clockwise direction. Okay, So since the diagram is not given, you can take it like anti-clockwise. In this case, I've taken the current in the anti-clockwise direction. I hope you are able to visualize it, right? So this point is X, and I am considering a small current carrying element. Remember, Biot-Savart law is applicable only for a current carrying element, means you need to always have a DL. You cannot write it for the whole conductor at a single slot. So you can consider a current carrying conductor DL, and what is the direction of DL? Direction of DL is same as that of the direction of current. So this one, let me show it again, how I'm going to take it, visualize it. So what I've done is, I've taken this loop and the current is flowing in this direction. So when I see from this side, it is going to be in the anti-clockwise direction. When I see from this side, it will be in the clockwise direction. This is a very important concept, remember this. When I see from this side, according to the diagram I've taken, it is anti-clockwise. This is the one which is close to me, and this is the part which is away from me. Okay, so when I've taken it like this, the next important point is, I considered a small current carrying element here on the top. So when the current is going in this direction, at the top, what will be the direction of DL? The direction of DL will be towards me. Please, you also, what you do is you keep your hand like this. Okay, you can keep your hand like this and visualize it. Do it simultaneously. So take as if there is a circular portion on your hand, and when you keep your left hand like this and take it like this. So when you see the palm of your left hand from the right, okay, when you see the palm of your left hand from the right, assume that the current is flowing in the anti-clockwise direction, and at the topmost portion you are considering a small current carrying element. And how is the current carrying element going to be? So at the top, how will the current appear? As if it is coming towards you. Okay, so that is why if you look at the diagram, I'm going to draw it like this. I'm drawing a value like this. So when this is happening, what will at the bottommost point? What is going to happen at the bottommost point? So at the top, if the DL value seems to be coming towards you, how will the DL be at the bottom? The DL will be as if it is going away from you. So that is why if you see the arrow mark that is given in both the diagrams, the arrow mark that is given in the diagram in your textbook says that at the top it is coming towards you, at the bottom it is going away from you, right? So from the current carrying element, for you to apply the Biot-Savart law, from the current carrying element, you need to link it to the point P where you are trying to calculate the field. So let that point P be at a distance of R. That is what R means in the formula. Okay. So this is how it is going to be. And similarly at the bottom also it is going to be such a way. I'll draw it only for the one element. So this, let me say, this is the first element and this is the second element. Okay. So if you're clear till this step, I can proceed. Just give me a confirmation in the chat box. Okay. Yeah, that's good. That's good. Please visualize this. Okay. So the second element is going to be away from you. Now what we are going to do is, see, this is the trickiest part. Please concentrate. Due to this current carrying element, I'm using another color, see, observe. Due to the first current carrying element, I want to find out what is the direction of the magnetic field at point P. How do I do it? So whenever I say direction due to a current carrying element, there are two concepts that we can use. One is the concept of right hand thumb rule, and the second is the concept of cross product. Okay, so let's try to use the concept of cross product here, because it is difficult for me to show it here because it goes in the three-dimensional plane. Once I apply the cross product, then I will show you how to apply the right hand thumb rule. You people can try it at your end and see. Okay, so for taking the cross product, what I'm going to do is, see, I'm going to place the conductor like this, the current carrying conductor exactly perpendicular. I'm not placing, actual diagram is like this, but I'm placing it like this for the sake of finding the direction. So DL at this point is towards me. Okay. Now what I'm going to do is, this is the origin, positive x-axis, positive y-axis, towards me is positive z-axis. Okay. This DL is there, no? DL is towards me. So towards me is considered to be positive. Anybody? Positive what? Positive z-axis. Very good. So positive z-axis. So how do we find? See, this is going to be a rough work. Okay, whatever I'm showing here, this should be a rough work you do for any problem. So the direction is given by the cross product of dl vector cross r vector, where dl is the direction of the current carrying element. So in this case, the direction of the current carrying element is k cap. cross this r cap is the one which you need to choose it very clearly. Okay, so when you're doing this r cap, no, so when you're doing the r cap, what is r cap? From the current carrying element, there is a point p here. From the current carrying element, the r is like this. It is like this. Okay, so r is going to be in this way. What does it mean? So if it is in this way, you need to take the starting point of this as the origin. Means the current carrying element should be considered as the origin, and then this position vector is going into which quadrant? If I take, so I'm telling you two concepts here. Please observe. For taking the direction of dl, I'm taking the center to be the origin. First point to be noted for this concept alone. For taking the direction of dl for a circular loop, I'm taking the center as the origin. Whereas for finding the direction of r vector, I'm taking the current carrying element as the origin. Okay. So when I take the current carrying element as the origin, then this is going to be y-axis. If that's the case, this particular vector is entering into which quadrant? If this is the origin, positive x-axis.
Fourth quadrant.
Very good. It is entering into the fourth quadrant. Very good. So k cap cross, what is going to be the direction of fourth quadrant? What is I and what is j? Which is positive, which is negative?
X is positive, Y is negative.
X is positive, Y is negative. So I should write it as I minus j cap. Sir, you can ask me, sir, why are you not taking I into consideration? I told you there is only a rough work. My objective is only the direction. This is not going to give me the magnitude. Please don't get confused. My work is to find the direction in the shortcut manner, and using vectors, you will get an accurate answer. Trust me. Okay. So k cap dot I cap, k cap cross I cap minus j cap. If this is clear, can someone tell me what is going to be the answer for this k cross I, taking the anti-clockwise loop? I, j, k. If at all you don't remember, k cross I is j cap. No, it is j cap. K cross I is j cap. Anti-clockwise is positive.
Okay.
Yeah. Minus k cross j is going to be what? K cross j is clockwise.
Minus I.
So minus is very good. Minus I cap. So what is the answer you are getting? You are getting it as minus of minus I cap. Sorry, I'm not showing you the screen. Minus of minus I cap is going to be I cap cross, I cap plus j cap. So what is this I cap plus j cap trying to tell me? I cap plus j cap. So I is positive and j is positive. Which quadrant is it?
First quadrant.
First quadrant.
It is the first quadrant. Very good. Means since I took this point to be the origin, the r vector is like this. So r vector is going into the fourth quadrant, whereas I'm getting the resultant in the first quadrant. And remember one more important point: whenever cross product between two vectors, whenever you're doing the cross product between two vectors, the resultant is always perpendicular to both the vectors for which you're doing the cross product. I'm repeating it again. Please make a note if you don't know this. Whenever you're doing a cross product, because this whole chapter runs on cross product only. Okay, please make a note of it. When cross product is done between two vectors, okay, the resultant of the cross product, the resultant vector of the cross product is always perpendicular to both the vectors for which the cross product is done. Okay, now what is happening is, see, this is where I'm going to conclude saying that, I'll close this part, okay. I'm closing this. So this is where I'm going to say that my resultant at this point is going to be perpendicular to whom? Perpendicular to the r vector. Perpendicular to r vector is going to be in this direction. Why did I take this direction? Because I told you first quadrant, if you consider this as the origin, if you had considered this as the origin, the resultant would have been like this. That is the meaning of first quadrant, because I told this is the origin, x-axis to be visualized, y-axis to be visualized. This. So r vector is in the third quadrant, whereas the resultant is in the first quadrant. What I'm doing is, I'm drawing exactly a vector parallel to it. This is an equal vector to it. Please understand this. I hope you know what is the meaning of an equal vector. Equal vectors are the vectors which are in the same direction and magnitude as a given vector. So with respect to this vector, I'm drawing this as the equal vector. Is this concept clear? Is there any point you want me to explain again, which is confusing or something of that sort?
Sir, can you just wait for a minute so that we can copy
Yeah,
this?
I'll do it. Yeah, you can copy it. You can copy it. I just want to find out if there is any doubt.
No doubt, sir.
Okay, then just copy it. Okay, make this diagram clear and make a note of this direction also.
Sir, I have a
Yeah,
doubt.
tell me.
Uh,
Please tell your name and talk so that next time I get used to your voice.
yeah.
Naveen, tell me now.
Sir,
Naveen, tell me.
the R vector, sir, it is in the
Yeah,
fourth quadrant, right?
it is appearing as if it is entering into the fourth quadrant. See, here there is nothing like fixed origin. Okay,
Okay.
that is why I told it is a very tricky concept. So when I took the dl vector, what did I consider as the origin? When I took
The
the direction of the center of the circle is what I took it as the origin.
origin, yeah.
Okay. Whereas when I wanted to find the direction of r vector, I took dl itself as the origin. So when I take dl as the origin, I draw a free body diagram. Observe, this is the curved portion. If this is dl is towards me. If I take this point, if I assume this point to be the origin, then obviously this has to be my x-axis and this has to be my y-axis. And r vector was like this.
Yes.
So
Okay.
this is the first, second, third, and fourth. So r vector is appearing as if it is going into the fourth quadrant.
Yes, sir. Okay.
Okay, so when I did the cross product, what did I get? I got I cap plus j cap. I cap plus j cap is exactly in the first quadrant. So the cross product of this dl vector and r vector came out in this direction. I'm using a different color, observe. That is the main working principle of a cross product.
Okay,
Okay,
sir.
I hope, okay, yeah.
Yes, sir.
So if this is clear, the remaining part is simple only. So this is the trickiest part. Okay. So once you guys make a note of this direction, no, I'll erase this part because that is not a part of the derivation. So whichever I'm putting in box like this, no, you need to ensure that you're doing it as a rough work. Don't show it in the exam hall. Because in your CBSE paper, if you show this, they'll strike it off. So I'll tell you how you're supposed to write it in the paper also. This is only for your understanding. Yeah, please. Oh. Name? I'm not able to hear you. Can you come close to the mic? Sorry, no, just a minute. I'm sorry, I'm not able to hear you. Is there a possibility for you to come close to the mic?
Sir, I'm Sriharini.
Shriyarni, tell me.
Sir, can we take for the other element also, the second element?
Yeah, you can do that. You can do that. See, if at all we want it as a part of, if you want it as a small exercise, I'll just give you this task. Why don't you find the direction of the magnetic field at point P due to the second element and tell me. I'll just give you 2 minutes time. Whosoever is able to crack it, please let me know. Using the same logic, okay? Using the same logic, you people choose whatever you want as the origin. I'll not say whatever I've told as the origin, okay? You do it as a part of the exercise and tell me. And Shri, to answer your question, yes, we can do it. Okay, yeah.
Sir,
Yeah, ma. Who's this?
sir, Darshini, sir, can you repeat
Darsh.
the question again, sir? Because your voice is breaking, sir.
No problem. I'll repeat it. See, listen. I'm saying, so Shriyarni asked me a question saying that, sir, you found the direction of the magnetic field at point P due to the first element, dl. So this is the first element. I'm putting a tick. You're able to see?
Yes, sir.
Okay. So she asked me a question, sir, is there a possibility for me to find the direction of magnetic field at the same point P due to this element? I told yes, there is a possibility. And I gave a task saying that using the same logic, which I've done here, I did a rough work in the box, right? So I told using the same logic, why don't you people find and tell me the direction?
Yeah, okay, sir.
Okay? Yeah, good, right. If anybody finds out, you can
I
unmute
cup minus
yourself.
j cup.
So y is vector written as, because it is entering into fourth quadrant, Kailash. Now who answered it? Is it Rohit?
Yes, sir.
So what did you say? You told?
I cup minus j cup.
That's right. Good. That's right. See, if you're able to do, it's fine. If you feel it is tough, I'm ready to do it. If somebody is willing to volunteer and tell me the directions, even if it is wrong, I don't mind. You can make a try. Anybody willing to? Okay, I'll do it. Now listen. Since dl vector for the first element was towards me, obviously as I told you the logic, the dl vector at the bottom is supposed to be away from me. So direction, this is for the second element, right? So the dl vector cross r vector is going to give me the direction of magnetic field. So dl vector at the bottom is going to be away from me. Away from me is obviously going to be minus k cap cross. If I take this current carrying element to be the origin, means when I'm doing it for the second element, I need to take the second current carrying element as the origin. If I take it as the origin, then if I take a curvature like this, then the r vector is going to enter into which quadrant?
First.
First quadrant. So what am I supposed to write? I should write it as I cap
I
plus j
plus
cap.
J.
Am I right? So minus k cross I, k cap cross I cap. So k cross I is going to be anti-clockwise. So it is going to be minus j minus k cap cross j cap. So k cap cross j cap is going to be in the clockwise direction. So it is going to be minus I cap. You already have a minus sign. So minus of minus I cap is going to be plus I cap. So what is the answer? It is going to be I cap minus j cap. So it's, yeah, you're right. So I cap minus j cap is going to be in the fourth quadrant. So fourth quadrant means it is supposed to be like this. If I take this to be the r vector, and remember that the distance will be the same, because when you take this point, no, that point will be like the slant height of a cone. So the distance is going to be the same, and it will be like this. So this is going to be the value of dB vector due to the first element, and this is going to be the value of the dB vector due to the second element. Right? So I hope it is clear. Yes?
Sir,
Yeah, tell me.
sir, could you explain that part why it was I cap plus J cap? I didn't understand that part.
Which part? This part? Huh? This part.
I
put
cap,
it
yeah, yeah.
I cap is j cap because when you're taking the direction of r vector, see dl vector, you have found the direction. For finding the direction of dl vector, the center should be taken as the origin. See, all the theory that I'm telling is my method only. Okay. If you have a different approach, you can think about it. But I think like this, I'm just sharing my thoughts. And r vector, what I do is whenever I want to calculate the direction of r vector, I take the current carrying element itself to be the origin. When I take the current carrying element to be the origin, then this is going to be x-axis, this is going to be y-axis. Virtually, right? There is no proper x-axis and y-axis. Virtually, this is how it is supposed to be. If this is taken as x and y, this r vector is entering into which quadrant? That is my question. Now, whosoever asks the question, can you answer it? R vector, it is entering into which quadrant?
Okay, so got
According
it.
to the first quadrant. That is why I took both to be positive. That is the reason. As simple as that.
Yes.
Okay. So you just have to look at the coefficient of I and j. That's it. Okay. So this diagram is a little bit complicated. To make it simple, I'll draw the final version of it. So you have a current carrying loop. So the current is flowing in the anti-clockwise direction. Right. You have the center here. So this is the point P. This is DL. This is DL and this is DL. So this is going to be inside and this is going to be outside. So what I'm doing is I'm taking this point to be at a distance r. Okay, and this distance is x. And dB vector is like this point. Okay. In a similar way, for the bottommost point also, I've taken something like this. This is r. Then the dB vector here is going to be in this direction. See, this is not the one that is given in your textbook. I'm doing a different approach. I'll tell you. Okay. Now the first and the foremost step is writing what is going to be the magnetic field due to one of the current carrying elements. So due to one of the current carrying elements, what is going to be the magnetic field? dB. I would first always make it a practice, you write it in the scalar form. Don't be in a hurry to write it in the vector form. So dB is equal to mu naught divided by 4 pi. This is the formula, I into dl into sine theta, the whole divided by r square. I hope this is clear. So mu naught is the permeability of free space. Mu naught by 4 pi is the constant that we have introduced. I is the current flowing through the element. dl is the length of one of the current carrying elements, and sine of theta. Sine theta means it is the angle between dl vector and r vector. I'll come to this point. We need to find that also. It is the angle between the dl vector and r vector, and r obviously represents the distance between dl and the point P. Okay. Now let's visualize. Again comes a small tricky part. Please concentrate again. So I've taken it like this. So this is dl. Okay. So if I take this to be dl, it is towards me like this. Am I right? So dl is going to be tangential to the surface. That's what I've done. So dl is towards me. If I take this to be the r vector, if I take this to be the r vector, okay, I'm repeating it again. dl is tangential to the surface. So I have no option to hold it. So please visualize it. dl is like this and dr is like this. Okay. So what is going to be the angle between them? Sorry, I'm going out of focus.
90.
Yeah. What is the? It is perpendicular. Okay. It is supposed to visualize. It's not possible to visualize in two-dimensional. So whosoever told the answer good, it is 90 degrees. So what should I write the value of theta as? So I would suggest this derivation you write step by step along with me, so that you're not confused. You don't wait for me to stop. Okay. So it is clear. So what is the angle between dl vector and r vector? Theta is equal to 90 degrees. Okay. Then what will be the value of dB? dB will be equal to mu naught divided by 4 pi into IDL. Okay. Sine 90 degrees divided by r square. This will be mu naught by 4 pi IDL divided by r square. Let this be equation number 1. I hope it is clear. Right. Now what I'm going to do is, I will take this angle to be phi, because the reason why I'm taking it to be phi is because this dB, if you observe the direction of dB, it is neither along the horizontal completely nor along the vertical completely. Okay, it is neither along horizontal nor vertical. So I need to resolve it into components to find out which components are going to get cancelled. Okay. So if I take this angle to be phi, this angle is also phi, because both the dls are symmetric with respect to each other. Since they are symmetric, both the values will be phi. Okay. Now what I'm going to do, observe clearly, I'm drawing a perpendicular here. Okay. If this angle is phi, then how much will this angle be? It is going to be 90 minus phi. Right? If this is 90 minus phi, and remember, r vector and dB vector are again perpendicular. So I'm drawing a shape C. R vector and dB vector are perpendicular to each other. If that is the case, out of the perpendicularity, 90 minus phi is gone. Then how much will this angle be? It will be phi, and I'm extending this line. So what is going to happen? This line and this line are perpendicular again. So if this is phi, this is going to be 90 minus phi. Okay. So I'm following the symmetry. So 90 minus phi, this is also going to be phi. Now this dB can be resolved into how many components? It can be resolved into two components. What are they? So this dB is what I'm trying to talk about. This value is going to be dB cos phi, and this value is going to be dB sin phi. Okay, similarly this dB will be dB cos phi, and the horizontal will be dB sin phi. Okay, since both the vectors are in the same direction, I have drawn two arrow marks. Now tell me which vector is going to remain and which vector will obviously get cancelled out.
Will get cancelled.
Cos will get cancelled.
Cos phi obviously will get cancelled because both the vectors are in equal magnitude and opposite direction, whereas dB sin phi is going to get added. So the required magnetic field for us at point P is not dB. It is the sum of dB sin phi and dB sin phi. Okay, so this is where you need to be careful. So the total magnetic field required at point P due to whom? Due to the two elements alone. I'm talking about two elements is going to be dB dash. So dB dash is equal to 2 times dB sine phi. I hope you people understood why it is 2 times, because there are 2 dB sine phi to the rightward direction. So I made a note of it. So it is 2 times dB sine phi. So 2 into, in the place of dB, I'm going to substitute this value, mu naught ideal divided by 4 pi r square. So mu naught ideal divided by 4 pi r square into, for me to find the value of sine phi, I need to consider a right angle triangle. So what is the right angle triangle I'm going to consider is, I'm going to take the triangle AOP. Okay, and one more point is, the radius of the circle is going to be A. So there are three terms. Remember, R is the distance from the current carrying element to the point P, A is the radius of the circle, and X is the distance from the center to the point P along the axis. That is the axial distance. Okay, there are 3 points. I'm repeating it again. A is the radius of the circle, R is going to be the distance from the current carrying element to the point P, and X is the axial distance from the center to the point P. I hope it is clear. Right. If that is the case, if I take the triangle AOP, I'm drawing a free body diagram of it. Observe. A, O, and P. Angle O is 90 degrees. This angle is phi. Right. This is A, this is R, and this is X. Now, if I ask you what is sine phi from the basic trigonometry, what are you going to say?
A by R.
Okay, that's easy, right? So 2 into dB. In the place of dB, I'm going to write it as mu naught by 4 pi. Sorry, I erased it because I wanted some space. So ideal divided by R square into sine phi. Yes, as you people told, it is going to be A divided by R. But what is R in terms of A and X?
A
Sorry?
square plus X square.
A square plus X square under a root. Right. So 2 into, see, this R square and R will get multiplied and it will become R cube. Am I right? So 2 times mu naught ideal into A divided by 4 pi R cube. I'm writing it like this. So what is this all about? This is all about the magnetic field due to only two current carrying elements. Right? Now I need to find due to the whole length. So dB, this value, I'm writing an extra step again, the same step repeated. 2 times mu naught I into dl into A divided by 4 pi r cube. Now what is going to be the total magnetic field? The B dash is equal to the integral of what? 2 times mu naught I dl into A divided by 4 pi r cube. That r I will substitute it. So there's going to be 2 will get cancelled. So what are all the parameters I can take out? Mu naught I divided by 2 pi into A can be taken out. Okay. Into this r cube can also be taken out, because what are you trying to integrate with? You're trying to integrate with respect to L, right? But what is the value of r? You people told me it is root of a square plus x square. So r cube will be a square plus x square the whole power 3 by 2. Please make a note of it. So in the place of r cube, I am going to write it as a square plus x square the whole power 3 by 2, and this a square plus x square has no term related to L. So that is also a constant. So what is the only variable that is getting integrated inside dl? So how many terms are there? How many terms have come out? Let's count and see. Mu naught, one term, I, yes, a, 2, pi, a square plus x square the whole power 3a by 2. There is only one term that is left out inside. Now what are the limits we need to choose for dl is, see, this is the law, this is the rule you need to follow throughout physics, not only for this particular topic, you can do it for anything. So this dl limits alone, I'll tell you how you are supposed to choose. If you take this to be, so I'll show you from this side. I've taken a dl here, I've taken a dl here also. Okay. So let's say I'm trying to take all such dls on the left hand side. So this dl is there, no? Let's say this dl is moving in such a way that it is moving in the left hand side. It is moving in the anti-clockwise direction. Okay, anti-clockwise direction. Then what will this dl do? This dl will also still keep moving in the anti-clockwise direction. Repeating it again, please observe. This dl is going to move in the anti-clockwise direction. This dl will be moving in the anti-clockwise direction. This dl will also move in the anti-clockwise direction. So each dl is covering a circle. It is covering a perimeter of how much value? Sorry.
By R.
Pi. It is not r. I wanted. It is pi.
Pi L. L.
Pi a, because here the radius is a. It is not. Okay. So what should I write? See, here, this is a tricky part again. Okay. Had I considered only one dl, okay. Had I considered, see, because I'm writing the magnetic field, I wrote it 2 dB sine phi, because this element plus this element. Had I considered only one element, then what should I write? I should have written it as 0 to 2 pi a. If you consider 2 elements, you have to write the half of it. For example, if I considered 4 elements, then what would have been the answer?
Pi A by 4.
Pi a by 2. Because it will come from here to here, no, it will cover a radian of pi by 2. There. Padma, think about it.
Yes, sir. Got it.
2 pi a by 4. See, the total circumference divided by the number of elements. That is going to be the limiter. Okay, that is the trick. So if I take it in this way, then I should write it as 0 to pi into a. Please be very careful. You will have a high tendency to write it as pi r. Because we are used to radius as r, it is pi a. It is because I am purely following it is because of the book notation. Okay, so please be careful. Mu naught I into a divided by 2 pi. This is the simplest integration you can do. Here nothing to do with the integration. It's all about the directions only. Integral of dl is obviously going to be L from where to where, 0 to pi a. Right. So this is going to be mu naught I a divided by 2 pi into a square plus x square the whole power 3 by 2 into integral of L is going to be pi a. This pi and pi is gone. A and a will get multiplied. The answer will be mu naught I a square divided by 2 into a square plus x square the whole power 3 by 2. This is the required answer. I hope it is clear. So this is the required answer, and you are expected to remember this formula because in the next chapter you have a concept called as solenoid. At that time we will use this result to prove that it is a magnetic dipole. So please have this in your mind. This formula has to be remembered. And one common mistake that happens is just because it is a circular loop, many students think that there will be a pi in the denominator. There is no pi for it. There is no pi expression at all in this. There is no pi term at all in this expression. So please be careful about this one. So this is going to be the total magnetic field. Okay. So I hope you have written along with me. Just make a note of it. I'll give you 2 minutes time. Just make a note of it. Anyways, after the class, I'll share this notes also. If there is any doubt, you can get it clarified. You can yourself and ask.
So if we need to find the field at the center of the disk of the ring, then do we just put yeah?
Are you saying center of the disk?
The center of the loop.
Okay, you want to find it at the center of the loop, then you need to put it as x is equal to 0. Because axial distance will be 0, right? That's it.
Yeah.
Okay. So there is an important observation also, I'll tell you. That's a good question you have raised. I'll tell you what you're supposed to do, what mistakes people generally do. I'll come to that point. So you can make a note of it, guys. So I'm not sure till where you have written. If anybody can let me know, I will show you that page. Or if you have completed, please let me know in the chat box.
So can you scroll a little up?
Yeah, sure. Till where did you write it?
Fine, sir, fine. Yeah.
Okay then. Yeah, right it. So I'm switching off my video. Completed, sir. Okay. We'll just wait for 5 minutes. Ashish, what is K cross I is J cap? K cross I. K cross I is minus J cap. Ashish. So someone has to tell me, or else I not know where you people are. So can I scroll it down? And there is a very, very important concept. Please ensure you practice it again. Because see, now you might feel you have understood, but I've seen many people doing mistakes. Okay. Please practice it. Right? So assuming that you people have completed, I'm going to the case, the special case. So the special case here is magnetic field due to a circular coil at the center. So magnetic field due to a circular coil at the center. So if it is at the center, what am I supposed to do logically? The point P has to coincide with point O. If that should happen, I should simply substitute the value of x as 0. Right? When I put the value of x as 0, the above expression, then I get mu p is equal to mu naught I a square divided by 2 into a square the whole power 3 by 2. This 2 and 2 will get cancelled. So I'll have mu naught I a square divided by 2a cube, a square, and this will get cancelled. Answer is mu naught I divided by 2a. If you observe this result, no, it is similar to what we have discussed in the previous class. Can someone tell me what it is? It is very much close. And that is a mistake I see always.
Infinite wire.
Due to an infinite wire, when you take the point P where?
At a distance A.
You take it at a distance A and you take the point P somewhere in between the ends of the wire. See, there are two scenarios I told you for an infinite wire also. If you take, I'll show you that. I think I can. So for infinite wire also, I told you two scenarios. If I take the point P at one of the ends, you're able to see this. If you take the point P at one of the ends, it is mu naught I divided by 4 pi a. If this point P is somewhere at the center actually doesn't exist for infinite length wire. Center in the sense I'm trying to say somewhere between the ends. That is going to be 2 pi a. So what the most commonly made mistake is here it is mu naught I by 2 pi a, no? If you look at the result for a circle, that is mu naught I divided by 2a at the center. Okay. So one common mistake our logic tells us is that because you have a circle, you should have a pi in the denominator. And because it's a line, you should not have a pi. But it is exactly the opposite. Okay. I hope I made this point clear. This is a very, very important point to be kept in your mind. Don't make this mistake. So B is equal to mu naught I by 2 pi a is applicable for a line current carrying conductor, okay, or a linear current carrying conductor. For a circle at the center, there is no pi that is going to exist. And one more thing is here, A is the perpendicular distance from the current carrying conductor to the point. In this case, A stands for the radius of the circular loop. Okay, so these two are the very, very important points. Please make a note of it. Right. So assuming that you have completed, we'll go to the next concept.
Sir, can you just repeat?
Just open it. Which part should I repeat?
Like you told there are two important points to remember. Right?
Yeah. See, I'll tell you. See, you're able to see my sheet. I've shared it. Yeah. See, there are two formulae. One is mu naught I divided by 2 pi a. This is for a linear current carrying conductor. And the formula we saw just now is mu naught I by 2a, which is at the center of the circular loop. Okay. So I told you our logic will tell because you have a circle, you will have a pi here, but pi is not there. For a circle, there is no pi. For a line, there is a pi. That is what I'm stressing on. Okay.
Yes.
Okay. You have to go in the opposite directions. That is what I'm trying to say. Okay. Now, what we will do is, I'll just try to explain the concept. See, this concept which I'm going to explain is mostly asked for the competitive exams, but here and there sometimes I found it in the CBSE paper also. I don't want you to lose the marks, so I'm just trying to give another logic to find out. So this is the circular loop. So when I put it in a plane, right, if this is going to be the center, what is going to be the magnetic field at the center? Just now we saw. So if the current is in the anti. It can see current can be in any direction, guys. Please. Current can be in any direction. You have nothing to do with the direction of current, but the value is going to be mu naught I divided by 2a. Okay. Can someone tell me what is going to be the direction of magnetic field at the center?
In this case, it's positive.
Positive k cap. Very good. Means it is towards us. So if I need to put a direction, I'll put a dot and a circle around it. If suppose the current is flowing in the clockwise direction, then what would have been the direction of magnetic field at the center?
Minus k.
Minus k.
Very good. It is going to be minus k cap. That's it, right? So what I'm going to do now is, see, this is the value of the magnetic field due to the whole length of the circular part. Now, if I restrict it to a semicircular part, then what would have happened? You're able to understand?
Still the
So
same.
if I reduce it to a semicircular part, if I ask you what are the magnet, I'm cutting this wire into two parts. Okay, I'm cutting the wire into two parts. I'm still concentrating on the center. I'm asking you calculate the, see, current is still the same potential difference is applied. Every other story is the same. The radius of the semicircular track is the same. But my question is, what is going to be the magnetic field at the center for a semicircular loop?
Sir, it will be into half
mu
the
naught I by a.
It should be mu naught I by
4.
4a. Okay, that's what our logic is telling. But what, see, I will just do a small manipulation in this formula. Please observe it clearly. I'll just do a small manipulation in this formula in terms of radian. Please observe it clearly because I want to create one formula. So what I'm going to do is, I'm writing it as mu naught I by 2. I'm just going to multiply a pi and compensate it with a pi. So this formula and this formula, are they both the same? Logically, they both are same, right? So mathematically, at least they are same. Now what I'm going to do is, see what is the angle made by the circle at its center in terms of radian?
2 pi.
2 pi, right? So I have a pi here. Instead of pi, if I want to make it as 2 pi, then what should I do mathematically? I'll multiply and divide it with 2. So logically, that's what I'm going to do. I'm going to make it as mu naught I divided by 4 pi a into, I'll write it as 2 pi. So can I make, see, this mu naught I by 2a formula, can I make it and manipulate it like this according to my convenience? Whenever there is a curved shape that is in the form of a part of a circle, I'll correct myself. Whenever there is a part of a circle due to which you are asked to find the magnetic field at the center, then can I put the formula like this? Mu naught I divided by 4 pi a multiplied with this 2 pi with respect to circle is what? It is the angle made by the circle in one complete rotation. Am I right? Into 2 pi, right? So instead of 2 pi, can I write it as theta? Can I write it as theta? Where the theta is going to be the radians that I'm going to substitute. Right? Am I clear with this? Is there anyone having a doubt? I did nothing. I manipulated this particular formula into this thing. Okay.
Sir,
Yeah. Someone is asking it out. Yeah, please.
sir, this will be for a circle only, right?
This will be for a circle or a part of a circle.
Okay, sir.
Okay. See, had it been a circle, what will be the value of theta that you're going to substitute?
2 pi.
2 pi. That's what I'm trying to say. So what I'm trying to say is, I'll actually a manipulated formula. Now I'll write the steps clearly. Please make a note. Magnetic field at the center of a circle is equal to mu naught I divided by 2a. Okay. This can also be written as mu naught I divided by 2 pi a into pi. This can also be written as mu naught I by 4 pi a into 2 pi. This 2 pi represents the angle at the center of the circle. Am I clear in this? So if this is going to be the case, then for any circular portion of the loop, for any sector Can I put it like this? For any sector, the magnetic field at the center, this formula is applicable only for the center. Don't do it for the axial point. For any sector, the magnetic field at the center will be equal to what? Mu naught I divided by 4 pi a. What manipulation should I do here? In the place of 2 pi, I need to replace it with theta. Where theta is what? Theta is the angle subtended by whom? By the arc at the center. Okay, so theta is the angle subtended by the arc at the center. Can I put it like this? Convinced? Everyone? Am I clear? Right. See,
Yes,
if you do
sir.
2-3 examples, you will understand. This just a mathematical manipulation, nothing else I'm doing. So, had it been a circle, I put theta as 2 pi. So, when it became a semicircle, this is still a, this is still I. Then what will be the value of b? Mu naught I divided by 4 pi a. In the place of theta, for a semicircle, what should I write? What is pi radius? Pi. That's it. This and this will get cancelled. It is mu naught I divided by 4a. See, the answer is same, but the logic is different. The logic you people would have used is, for a circle it is becoming half, I'm writing it as half of the initial value. But I'm trying to write it in terms of angle because this formula will save you whenever you have an angle other than the other than this pi or something, like you, if you have something like 2 pi by 3 or something, okay, or 120 degrees or something of that sort, that time this will save you. Okay, now if I have a quarter circle, then the value of b at point O would have been mu naught I divided by 4 pi a. You people tell me, you know the answer. So what is the angle?
I by 2.
Pi by 2. Pi and pi will get cancelled. It is going to be mu naught I divided by 8a. In a similar way, if I have an arc which is making some random angle, I don't know what angle, theta is equal to, let me write as pi by 3, then what should I write? B is equal to mu naught I divided by 4 pi a into pi by 3. This and this will get cancelled. Answer will be mu naught I divided by 12a. As simple as that. Okay. So this is how the manipulations are done. Okay. As I told you, this is mostly tested only in the competitive exams, but here and there I have found it in the CBSE papers also. If at all it comes, let's say it's a 1 mark question, you need not lose it, right? If anything is not clear, please get clarified. If you're clear with this, we can do few example problems and then we can proceed to the next concept.
Yes.
Okay, clear. Okay. If at all you want to make a note, please let me know, or else I'll proceed with the problems. Anybody wants to make a note? Or you can wait till the class is over, where I'll be sharing the sheet and you can copy. So for as of now, what I'll suggest is, for this problem solving part, make a note of this formula. Mu naught I divided by 4 pi into theta, where theta is the angle subtended by the arc at the center. Okay. So let's frame our own questions. Okay. Now what I'm going to do is I'm going to do a combination of the linear and the circular motions. Okay. So I'm going to make a combination of linear and circular motions. You have to find the magnetic field due to the system at a given point. So let's see what it is. Write down the questions. Find the magnetic field due to the below systems. Find the magnetic field at point O due to the given configuration, you can say. This is a different way of arrangement, that's it. Due to the given configuration. The first question. What I'm going to do is, I'll put it like this. So this is I. Okay, let's make it simple. Wait. I'll make it simple. First, okay, you need to find it at point 2. The current is flowing in the clockwise direction. The current flowing through all the conductors is I. Okay. When I say find the magnetic field, you need to find it along with the direction. I want the answer along with the direction. So same thing, the current is flowing in the anti-clockwise direction. Now what is going to be the scenario? Okay. Third. This is radius A, I. Here also the radius is going to be A. This is radius A, current is flowing in this way. Okay. Find the magnetic field at point O. Here the current is I, here also the current is I. So let's take the diagram. Okay. Okay. See, all the straight portions that you're seeing at this point and this point are infinite length. Okay. This is also of infinite length. Our work is to find the magnetic field at the point O due to the different kinds of systems. So this is A. Let's say this is also A. Just think, you will get the answer. I can give the answer.
Answer.
Done? All the 4 are done? Rohit?
Yes.
We'll just wait for 5 minutes, then we'll start discussing. We'll start doing it. See, how to do the first one is, Rohit, can you tell me?
The first sum, the answer is not I by 4a minus k cap.
That's right. But how to proceed? That's what is more important.
Yeah.
What is
So
our question?
we know the formula for the semicircle. This mu naught I by 4 pi a into theta, where theta is pi over here.
Okay, mu naught I by 4 pi a into pi. So you wrote it as mu naught I by 4a. Okay.
Yeah,
That's it.
and since no, we know the point is making 0 degrees with the ends of the straight wires. So that's zero.
That's
So
right. Very good.
total
Very
will
good.
be mu naught I by 4a.
That's right. So this is a three conductor system. So the first conductor is a straight conductor, the second is a semicircular conductor, and the third is again a straight conductor. So whenever the conductor is passing through the point where you're trying to calculate the field, the distance is going to be 0. Or you can say the angle made is 0. You can take in any of the ways. So actually, to be more specific, angle is 0. Okay. So when it is, if a conductor is about to pass through any point where you're trying to calculate the field, the conductor, the magnetic field due to that particular system is 0. So B1 is 0. Similarly, B3 is 0. B1 is magnetic field due to the first conductor. B3 is magnetic field due to the third conductor. So the magnetic field due to the second conductor is going to be mu naught I divided by 4a. Since the current is flowing in the clockwise direction, the answer will be minus k cap. So the total magnetic field will be equal to B1 vector plus B2 vector plus B3 vector. So B1 vector is going to be 0 plus B2 vector is going to be mu naught I divided by 4a into minus k cap plus this again 0. So the required answer is mu naught I divided by 4a in the direction of minus k cap. If I do the problem in a similar way, what will the answer for the second one be? So if you look at the
Mu naught
second
I
answer,
by 4a
by 4
k cap.
it is the same thing, only difference is going to be the direction. So B is equal to mu naught I divided by 4a in the direction of k. Right? So this is one way. So third is, where is it? Third is very, very easy.
mu naught I by 16a.
That's right. So this is 1, 2 and 3. Magnetic field due to the first conductor, again 0. Magnetic field due to the second conductor is going to be mu naught I divided by 4 pi. It is a part of the circle into angle is 45. So it is going to be pi by 4. Pi and pi. That's right, mu naught I divided by 16. Very good. And B3 is going to be 0. So the total magnetic field will be mu naught I divided by 16a in which direction?
Minus k cap.
Very good. So the magnetic field is going to be mu naught I divided by 16a in the direction of minus k. Right. So fourth one is slightly a tricky one. Let's do it. I'll draw the diagram again. So what was the answer here? Mu naught I divided by 16a. 16a in the direction of minus k. So for the fourth one, let's see. The conductor is like this. This is one. Second conductor, third conductor, fourth conductor, and fifth conductor. Am I right? No confusion in this, right? So this is going to be A. Oh, actually, I made a mistake. I should have given you some distance. Let's say this length is A. So let's say this length is going to be A. Okay. So what is the magnetic field due to the first conductor at point O? So what case is it going to be? I told you one is an infinite length conductor. For an infinite length conductor, where is the point O? Is it considered at the center or one of the ends?
Of the ends.
One of the ends.
One of the ends means what is going to be the answer? Mu naught I divided by 4 pi into the distance. Distance how much? Distance is 2a. Distance is 2a. Now, can someone tell me what is going to be the direction of it?
Minus k cap, sir.
Minus k cap.
Very good. It is minus k cap. That's right. So B2 is how much? 0, because it is passing through the point where you're trying to calculate the field. Similarly, B4 will also be 0. Now, what will be the value of B5?
Mu naught I by 4 pi
I
2a
by 4 by 2a plus k.
plus k cap.
It is going to be plus
Minus
k
k cap.
It is
Minus-
minus k cap. It is minus, sorry, it is minus k cap. See, don't make this mistake. Just because the currents are in opposite direction, magnetic field will be in opposite direction. No, because here it is cross product. Please be careful. So B3 is how much? Mu naught I divided by 4A. This is also in the direction of minus A cap. So what is going to be the net magnetic field? Net magnetic field will be equal to B1 vector plus B2 vector plus so on till B5 vector. So what will the answer be? Mu naught I divided by 4 pi into 2A. This coming out twice plus mu naught I divided by 4A. This coming out once. Everything in the direction of minus K cap. This is going to be the required answer. I hope it is clear. So 2 and 2 will get. Yeah, tell me.
Sir, can you explain the third one, sir?
Third is which one? B3, yeah?
No,
This
sir,
one.
third sum. That quadrant.
Third is which one? This one.
Yes, sir.
That's why I gave you the formula. No, it is mu naught I divided by 4 pi A into the theta at the center. Angle at the center is 45 degrees. 45 degrees is pi by 4 radian. This is the formula I used. Where is it? You remember, no? This is the formula I used.
Yes, sir.
Yeah. That is why you got 16.
Thank you,
Yeah,
sir.
yeah. So mu naught I divided by 8 pi A. Sorry, not 8 here. 4 pi A only. 2 and 2 got cancelled. Okay. So mu naught I divided by 4 pi A plus mu naught I divided by 4A, everything in the direction of minus K. So this will be the required answer. Okay. So easy, right? Yes.
Sir, one doubt.
Tell me. Yeah, tell me.
Sir, for finding B1 and B5, you took it from the end, right, sir? Based on what? I didn't understand that part alone.
Yes, this part. So
Yeah,
the
from the.
application of method, you remember this one, right?
Yes,
This
sir.
one, this part. This is the formula used.
Okay.
So when I drew the diagram was like this. The circular part, this is the point. So with respect to this point is at the end only. No?
Yeah,
The
sir.
straight conductor, the first conductor is ending here. Okay, that is why I took it as one of the ends. So that is where you need to be very careful.
Okay.
Okay. So this is how we solve the problem based on. This is how we solve the problem based on circular quotient as well as a straight current carrying conductor or the combination of them. Okay. One rule I will tell you, this will help you to find out the directions for circular quotients. Okay. This is called as clock rule. This is called as clock rule. So before I explain this rule, I'll ask you a very basic question. In your 10th grade, you would have learned that. If I ask you for a permanent magnet, what is the direction of magnetic field? North to south where? Magnetic field lines, do they form closed loop or are they open loops like electric field lines?
Close to it.
They form a closed loop, right? So when you take a permanent magnet, it is from the north pole to the south pole, outside the magnet, and inside the magnet, how is it going to be?
South to north.
Inside it is going to be so south to north. I'll just draw the diagram. I hope you will be able to recollect this concept. If I have a permanent magnet like this, north pole is like this, south pole is like this, the current flows in this way. So north to south outside the magnet and south to north inside the magnet. So whenever you have two poles, okay, whenever you have two poles, that particular object is called as a dipole. Di refers to two, pole refers to polarity. So two poles put together, we call it as a dipole. If it is a magnet, we call it as a magnetic dipole. If it is due to the charges, we call it as an electric dipole. So this is what is going to be a magnetic dipole. So for a magnetic dipole, what is going to happen? The magnetic field outside the magnetic dipole is going to be from north to south, and inside it is going to be from south to north. Am I right? So when this is the case, I'm going to say a concept, make a note of it, write it down. Every current carrying loop acts as a magnetic dipole. Every current carrying loop acts as a magnetic dipole. Okay. Let me explain what it means. Suppose I have a conductor in my hand. I have a loop. I have a coil which is having one turn. Okay. Since I told one turn, I just got a reminder. Just make a small note here. The concept which we discussed, we saw the derivation of mu naught I a square. So this formula is there, no? In this formula, this is the formula you are supposed to use for a circular coil when it has only one winding. Winding in the sense one turn, one circular turn. If there are n turns, if there are n, in physics, when I say number of turns, it is always capital. If you use smaller case, it is always the number density. So please be careful about it. That is a universally followed language. That is, there is no specific rule. It is for understanding purpose. If there are n turns, then magnetic field at the center will be equal to, then what manipulation will happen to the formula? If there are n turns, then what would have happened? The whole expression should be multiplied with a capital N. That's it. Okay. Then the answer would have been, that I make a note of it, mu naught capital N I a square divided by 2 into a square plus x square the whole power 3 by 2. This n will be an extra term. That's it. This is for one turn and this is for n turns. The same thing is applicable here also. If the coil is made up of only one turn, it will be mu naught I divided by 2a. If it is made up of n turns, it will be mu naught ni by 2a. That's it, as simple as that. Nothing outside it. Okay. So keeping this point in mind, what I'm going to explain is, if suppose you have the point I gave you is, I'm saying you have a magnetic, every current carrying loop. Okay. There are two words I'm using. Please be careful. Please make a clear understanding of it. Current carrying conductor and current carrying loop are not the same. Current carrying conductor can be an open conductor also. For example, a straight current carrying conductor. We cannot say a straight current carrying loop. That doesn't make sense. Loop means it should start from the same point and come back to the same point. So the loop can either be a circular one or it can be in some random shape like this also. It can be in any shape, but it should be closed. So this concept, when I told you magnetic dipole, you need to underline the word loop. Every current carrying loop acts as a magnetic dipole. Why it is acting as a magnetic dipole? Because it behaves similar to a permanent magnet. Let me explain why. Let's say the current is flowing in the clockwise direction and the current is flowing in the anti-clockwise direction. What is going to happen? I'm switching on the video, please observe. So the same loop, okay, the same loop, if say current is flowing in the clockwise direction, when you see from that side if it is flowing in the clockwise direction, when I am seeing the same current, it is going to flow in the anti-clockwise direction. Means within the same loop, depending on the perspective of the person who is seeing it, you can say there are two directions in which the current is flowing. If suppose you are seeing it, with respect to you, if it is clockwise, with respect to me, it will be anti-clockwise. Keeping this factor in mind, look at the way I'm going to draw the diagram. When the current is going to flow in the clockwise direction, that is, when you are seeing it, then this will appear like a north pole. Sorry, this will appear like a south pole. Let me draw this diagram. You put an arrow mark like this, you join both, it stands for S. So why I put the arrow mark like this is because parallel to this. I put an arrow mark parallel to this. Similarly, when I see the same conductor, for me, it will appear as if it is generating a north pole. Okay, observe. I'm drawing a line parallel to this. And when I join these two, it is going to be an N. Am I clear? So what I'm trying to say here is, if I have a loop like this, with respect to you, if you are able to see it clockwise direction, okay, I will be able to see it as anti-clockwise direction. Means, if this has a thickness, let's assume there are 5 more bangles kept like this. If this has a thickness, then it will act like a permanent magnet as if you are seeing the south pole, I am seeing the north pole. So what will be the direction of the magnetic field? The direction of the magnetic field will be from the north pole to the south pole outside the magnet, and inside the magnet it will be from south pole to the north pole. That is why till now whatever problem did, whenever the current was flowing in a clockwise direction for a loop, you always got the answer as minus k cap, because south pole will receive the magnetic fields, north pole will eject the magnetic field lines. I hope it is clear, right? That is why a single loop, a current carrying loop, is also called as a magnetic dipole, because you have north pole on one side and the south pole on the other side. I hope this concept is clear. Okay, how to find it out? There is the diagram, and this kind of a rule is what is called as a clock rule. And this is going to be the last topic. So I'm going to end the session with this. I'll just give you 2 minutes time. If there is any doubt, get it clarified. Okay. So,
Sir,
yeah, who's
sir, yeah.
Naveen.
Sir, actually, clock rule, like, why exactly are we considering the anti-clockwise as south pole and
No, clockwise.
clockwise as, sorry,
Clockwise.
yeah, clockwise as south pole and anti-clockwise, like why?
Because see,
Vice versa.
you have a mathematical reason for it also. See, when I take the clockwise direction, this is the direction of dl, and this is the direction of r vector.
Yes, sir.
Okay. So I am applying Biot-Savart law to this only to find the direction. So the direction is given by dl vector cross r vector. Dl vector is in the direction of I cap. R vector is in the direction of minus j cap. This is the origin. I cross j is going to be minus k cap. So into the plane. Into the plane means, see, if something has to be into the plane, if I put something like this, if I put it as into the plane, I switched off my video. If I put it as into the plane, okay, it is like this with respect to me. This is the clockwise direction, it is into the plane. Which pole out of the north or the south pole has the tendency to receive the magnetic field lines?
The south pole.
That is what I do. That is why I drew it as so. Okay?
Yeah.
Yeah, that's the reason. Okay, I guess others have other classes now. So I'm ending the session. So the recording will be uploaded. If you have any doubts, just go through it. If there are any doubts, get it clarified in the next class. And one more thing, please ping your attendance in the WhatsApp group so that we can make a note of it. Okay. Thank you. See you all. Bye.